you hear me?
Yes.
Okay. Yeah, thank for your time. Today I would like to talk about accelerating deep learning workload with Intel AI Analytic Toolkit and the third generation Intel Xeon Scalable processor. So the agenda we will touch upon is the first, we will introduce deep learning component from Intel AI Analytic Toolkit. So we will cover AI Analytic Toolkit, also the Intel Optimized Deep Learning Framework. We will also introduce Model Zoo. So using Model Zoo to do some performance benefit analysis. So that's the first section. The second section, we will touch upon accelerating AI performance on our third generation Intel Xeon server with Intel Optimized TensorFlow and Bfloat16. So we will talk about introduce the Bfloat16 acceleration on third generation Xeon server, and also give you a performance analysis by using Bf16 on third generation Xeon server. So first, let's talk about what is Intel AI Analytic Toolkit. So we would like to help the AI developer for developing their workload easily and get a speed up on our platform, either CPU or GPU. So we provide both deep learning component and also data analytic and machine learning component. So inside it, you can have Intel optimization for TensorFlow, Intel Optimize PyTorch, and also a low precision conversion tool, Model Zoo. For machine learning, you can get the XGBoost, Scikit-learn, Delphi, Pandas, and also some data accelerate data frame component like Modern. So you both machine learning, data analysis, and deep learning, we provide the related optimized package for you. Uh, so what you can get from the AI Analytic Toolkit is first, good performance. So we optimize performance for both CPU and future GPU. So right now, the DG1 or the ATS or Punkivachi Kyo. So that's the GPU architecture we will support soon. Not only that, we also give you lots of AI and machine learning related package inside the toolkit. So you can develop an end-to-end workload, including data processing and also deep learning, machine learning. And also we give you the conduct package or PIP package. So overall, you don't need to worry, integrate those package for your workload. We provide a toolkit. It will improve your productivity because you don't need to set up the environment by yourself. And we also give you some example, pre-trained model, and also some end-to-end workload. So let you start your development easily. So that's a couple aspect, couple benefit by using Intel AI Analytic Toolkit. And so let's look into the deep learning component of Intel AI Analytic Toolkit. So for the hardware, we support both CPU and GPU. So on top of hardware, we have one API performance library that they are one DNN and one CCL, which are programmed in C. So there is a C performance library. And on top of those one API performance library, we have Intel TensorFlow and Intel PyTorch, which are popular deep learning framework in Python. So both Intel TensorFlow and Intel PyTorch will be accelerated by the one API library. And on top of the framework, we also have some tool like Model Zoo, and the low precision tool. So Model Zoo will give you some benchmark and pre-trained model, let you easily get a understanding for the speed up among different model. For low precision tool, it can help you to quantize your model from AP32 to IN8. So those are on top of framework and help you to develop your workload easily on our AI toolkit. And we would also like to mention what kind of optimization we have inside Intel deep learning framework. So first, we have graph optimization. So our framework will look through your graph and try to optimize your graph by using fusion or batch normalization or optimize the memory allocation. Not only graph optimization, we will help you to have an efficient memory cache usage. So we will doing the blocking or data reuse, prefetching. So help you to reduce some cache misses or page 4, memory page 4. And moreover, everybody aware that Intel has a synced instruction set. So for those optimized framework, we will help you. Actually, we will using our performance library and do the vectorization for you. So you don't need to worry about vectorization by yourself. And our performance library will vectorize the deep learning code for you. So basically, our expert will look into the loop line and actually optimize vectorize the related code for you. And for Xeon server, there are lots of CPU cores. So we will make sure we utilize all the CPU cores by using OpenMP or MPI or TBB. So we'll try to have the good load balancing over different CPU cores. If you're interested in distributed deep learning, we will also help you scaling your deep learning workload well. So by using one CCL, that's our scaling performance library. So overall, we support not only Horova, but the PyTorch can also using one CCL as a backend. So we have these 5 aspect optimization. So let's look into the performance by using Intel Tensorflow. So in the left-hand side, the left-hand side diagram is a latency result. So lower is better. And we compare among Intel NKO DNN version with Eigen version. So basically, Intel NKO DNN version actually is Intel TensorFlow. So accelerated by Intel NKO DNN, which is renamed as 1DNN. So it's our performance library. So it's Intel TensorFlow. For Eigen, it's stack TensorFlow. So by default, stack TensorFlow using Eigen as its threading library. So we compare Intel TensorFlow with stack TensorFlow. The y-axis is the latency, the lower is better. The x-axis is different model. So as you can see, the latency dropped down from maybe 0.79 to 0.39. So basically, you have a lower latency. In the right-hand side, there's a throughput result. So we also compare Intel TensorFlow with stock TensorFlow. And right now, higher is better. So the y-axis is the throughput. The x-axis is different model. So you can see we have a throughput, we have a speed up around 1.6 to 2.7. So those benchmark are measures on top of Intel TensorFlow and using Intel Model Zoo. So Intel Model Zoo is open source project. So you can easily get those numbers, understand the benefit of Intel TensorFlow by yourself because it's open source and we have a pre-trained model. So people can easily try on their environment and understand the benefit of Intel TensorFlow. So we would like to also cover what is, we will also like to explain what is Model Zoo. So we have, for many popular open source machine learning model, we have a pre-trained model for you. So if you just want to run the inference and understand the speed up, you can use Model Zoo. There's lots of pre-trained model, and you can just run the command and get understand the speed up. And there are also lots of sample script for among different model like ResNet 50, BERT, YMD. So we try to provide the popular model inside Model Zoo. And we also have best practice. So inside the documentation, we have some suggestion and BKN about how to configure the OpenMP for the specific model. So we also have a step-by-step tutorial. So actually our tutorial we're using Model Zoo, so you can understand better when we cover the tutorial session. So purpose of the Model Zoo, we want to that user benchmark the performance of optimal model on Intel hardware and understand the benefit. So we just want to user get started efficiently running those pre-trained model or those simple model script easily, and then they can try to move their workload on top of Intel TensorFlow. So that is for Model Zoo. So before we jump into the tutorial, are there any questions so far? If no,
the main reason why Intel TensorFlow is different from the original TensorFlow?
so yeah, we covered those optimization. So there are lots of different aspects. For example, for vectorization, we actually support the latest vectorization instruction, including DL boost, which are available on the second and third generation of Xeon server. So the DL boost is a new AVX 512 instruction, which help to accelerate deep learning. So we are actually there are 5 aspects, 5 optimization category that we have inside Intel TensorFlow.
Okay, thank you.
Yep. So actually today, I think the second session, we will show you the performance analysis for DL boost on Bf16. So okay, so let's go to the tutorial. So the first tutorial, we want to show you the performance benefit of Intel TensorFlow. So we will actually using ResNet 50 1.5 model from Model Zoo, and we are running on Intel DevCloud. So if you just want to give a try on our AI Analytics Toolkit, you can register Intel DevCloud. So inside DevCloud, we will provide the support hardware like Intel second generation of Xeon server, and also you will have a Gen 9 on the DevCloud. So we also install those software inside the DevCloud, so you can easily try on our software stack with on top of Intel hardware easily. So you don't need to set it up by yourself. Uh, so overall from this tutorial, first we will show the speed up by using Intel TensorFlow, and we will using TensorFlow timeline to give you performance analysis on operation level. So let's look into the tutorial. Wait a minute. So first, I would like to mention about where you can get a tutorial. So we publish those tutorial under Intel Model Zoo. So I think we have the link in the slide deck. So overall, under the Intel AI models, it's Intel Model Zoo. So we have a performance analysis notebook. Right now, we publish 2 notebooks. So basically, you go to the documentation notebook performance analysis. You can easily get a notebook. That's the material we use today. So first, we have 2 notebooks. So first notebook, actually, we will help you to run the benchmark on top of Intel and stock TensorFlow. So you don't need to actually config any parameter. You just need to run through all the notebook cell. And the only thing you need to do is pick a topology, which you want to analyze. So first session for sure is run the benchmark on select Jupyter kernel. So you need to actually select Intel TensorFlow Jupyter kernel or stock TensorFlow Jupyter kernel. So no worry right now, we have a README for that. And then you need to select a support topology. Right now we support different topology like different ResNet 50 version, inference and training, DenseNet, YMD, large. So overall, once you select it, you just run through all the Jupyter cell. And you will actually run the benchmark for you, get the performance number, and also got the TensorFlow timeline file for you. So in the end, you will get the performance overall performance analysis. So right now we compare stock and Intel TensorFlow throughput. So the orange bar is Intel TensorFlow, and the blue bar is stock TensorFlow. And on DevCloud, we can get around 5.7 times speed up. So overall, the first notebook, you can easily run it on different platform. You can get how much, you can understand how much speed up you can have on your platform. So this is on DevCloud, so you should be able to see the similar speed up by yourself if you run on DevCloud. And second notebook, actually, we do some performance analysis on on TensorFlow timeline by using TensorFlow timeline. So the session 1.2 is about analysis the TensorFlow timeline between stock and Intel TensorFlow. So I would also like to roughly introduce what is TensorFlow timeline. So TensorFlow timeline it will give you the detailed information, time information about different TensorFlow operation. So you can understand how much time you spend on different operation. So we gather those information and do some analysis. So first, you should be able to get the comparison table here. So maybe it's too small. Let me enlarge it. So I hope it's big enough. Let me maybe. Okay. So first, you will have a table like list one. We will have more diagram, passing diagram later. But let's look into this table first. For the first column is operation column. So it's a different TensorFlow operation like fuse convolution 2D add value, max pool. The second column is the elapsed time from stock TensorFlow. And the third column is elapsed time from Intel TensorFlow. So we're using NKO-DNN as a performance library. So we use NKO as a postfix. And fourth column is speed up. So we compare the NKO Intel TensorFlow with stock TensorFlow and get the speed up for each operation. And third column is NKO operation. So overall, if this TensorFlow operation is accelerated by NKO-DNN, we will mark it as true. So you can understand which operation are accelerated by NKO-DNN. So we parsing this result and give you some diagram. So the first diagram, we compare stack and Intel TensorFlow, and we compare among elapsed time. So the y-axis is elapsed time. The yellow bar is stack TensorFlow. The blue bar is Intel TensorFlow. And as you can see, the most of the operation, the top, I think the top 3 hotspot, I think the top hotspot, you can see actually uh, Intel TensorFlow actually spent less time, much less than the stack TensorFlow. However, for the second top hotspot, the add operation, actually Intel TensorFlow may spend more time on this operation. So overall, we can understand most of our operation, we have a good speed up, but some operation, we may identify some performance degradation. So overall, by using this performance comparison, user may identify some problem and they can feedback to us. We can help to improve that. So, but overall, you can understand that we have lot of speed up on the top hotspot. So overall, you can get a good speed up on this model. And we also compare, we also show the diagram about speed up by using 1DN operation. So the y-axis is speed up, and the red line represent 1. So if the bar is higher than the red line, it means you have a good speed up. If the bar is lower than the red line, actually you may have some slowdown. So as you can see, the blue bar is 1DN operation. Most of the 1DN operation are above red line, so it means we have good speed up, except the add operation. So this operation, the user can actually give us feedback, and we can look into that. But you can look into the orange bar. Most of the orange bar are just below the red line. So it means the operation which are not accelerated by 1DN actually got some slowdown. So you can also see this pie chart. This show you the percentage of elapsed time among different operation. So you can easily understand which operation take most of time. You can understand which are the top hotspot. So for stack TensorFlow in the left-hand side, it spent 91% on the fuse convolution 2D. But for stack TensorFlow, user need to look into the convolution 2D for further optimization. But Intel TensorFlow, you can actually identify the first hotspot is add operation. It took 40% of your time. So that means if you switch to Intel TensorFlow, your hotspot is no longer fuse convolution 2D. Actually, you need to look into the add operation. We also understand on the previous bar chart diagram, the add operation, actually we have some slowdown. So combine this pie chart and bar chart and the previous bar chart, you can understand the add operation is the next optimization opportunity. So that is the Jupyter Performance Analysis Jupyter Notebook, and user actually can run on their environment. So on different hardware, you may see different result, but you can understand which is the bottleneck and which operation you may need to look into. So that is the first tutorial. Let's go back to the slide deck. So before we go back to go to next session, is there any questions so far? So if no, let's go to the next session. So for next session, we would like to mention about Bfloat16 on third generation Intel Xeon processor. So it's Bfloat16 also are part of our DO boost acceleration Bfloat technology. So first, we would like to overview what is Bfloat16. So it's another data type format, and BF16 has several advantages over AP16, which are also 16-bit data format. So first, BF16 can see as a short version of AP32, but it has the same exponential bit. It just have a smaller Mantissa field. So it actually have least significance 60 bit of Mantissa. But actually it's pretty enough for deep learning training tasks. And so that's why we also provide this BF16 support, because you will see a performance benefit by using it, and it also pretty enough for support a deep learning training task with good accuracy. So for Intel third generation Xeon server, we support BF16 by having coupled new BF16 instruction. So excuse me, let me close the window. So first, we have two instructions help user to convert to and from BF16 data type. And we also have one instruction to do the dark production of Bfloat16. So they are new instruction set added in the third generation Xeon server. And so let's look into the performance improvement on third generation Xeon server by using BF16. So in the left-hand side, it's a comparison among three models, and the x-axis is the performance improvement, and the y-axis is three different models. So we compare between second and third generation Xeon server. And for sure, third generation Xeon server, we leverage the new Bfloat16 instructions. So overall, you can see among different models, we get the speed up from 1.7 times to 1.9 times. So it's a comparison among different generation of Xeon server. But the third generation, we have Bfloat16 instruction support. Not only training, we also have a good speed on inference. In the right-hand side, you can see the Resnet 50 have a 1.8 times speed up, and BERT large, we have 1.9 times speed up. So overall, you don't need to change your model. You just switch to our third generation Xeon server with the Bfloat16 instruction support. You can have that kind of speed up. So same story applied to PyTorch. This is a number from PyTorch, but we did the experiment on third generation Xeon server. So we compare AP32 and BF16, but those experiments are conducted on third generation Xeon server on the same architecture. So as you can see, we have a speed up among, so the speed up ratio is in the fifth column. And you can see among different model, three different model, the training, we have a speed up from 1.4 to 1.6. So it's on the same machine, but using different data type. And for inference, for DORN, we also have a 2.8 times speed up. So if you're interested in more detail, you can actually look into the blog. We put a link here. So before we go into the tutorial, any questions so far? Okay, so for tutorial, we want to show you how to get how to do the performance analysis and understand the speed up by yourself. So we still using the Intel Model Zoo. We still using ResNet 50. We will do the training and inference, and we will compare among different data type for training and inference. So for training, we will compare among FP32 to BF16. For inference, we will compare among FP32 versus INA and FP32 versus BF16. So if you use pre-trained model for inference, if you just have a FP32 pre-trained model, you need to have using a quantization tool that we provide to quantize the pre-trained model to INA. But if you want to use BF16, you want to run your FP32 pre-trained model with BF16 data type, there's no quantization required. So we will mention about that later. So let's go into tutorial. So similar to the previous tutorial, we also provide notebook for you to compare among different data type. So you only need to actually
Louie?
okay. So you only need to pick up the topology you want to compare. So right now we have ResNet 50 supported, and we have inference and training. You just pick one. It's right now we support 16 and in A. Oh, maybe let me wait a minute. So and overall, and you understand actually you may choose in this case you choose ResNet 50 profiling inference, and you know that we support AP32, BF16, and INA data type. So this tutorial actually will run through those three different data type and give you the performance analysis among those data type. So first, for sure, you will get the overall performance analysis. So you can see actually for this diagram, the first bar chart diagram is the throughput, and the second is speed up. And we compare among three different data types. The blue bar is FP32, the orange bar is BF16, green bar is INA. So you can actually look into the throughput number, or just look into the performance speed up comparison. So as you can see, we have a speed up on LP32 and also on INA. So you got 1.5 times speed up by using BF16 compared to LP32 on the same machine using the same Intel Tensorflow, by just changing the data type. And you can have further performance improvement if you use thing in A. You see you can have a 1.7 times speed up by using in A. So basically, you can understand understand machine and understand the TensorFlow version. And then we look into the performance analysis. So we want to let user understand how much speed up among different TensorFlow operations. So let's look into the first comparison table, FP32 versus INA. So you can see the first column is the TensorFlow operation. Second is the elapsed time for the FP32 by using FP32. The third column is the elapsed time by using INA data time. And then we calculate the speed up by using INA. And the final column is if this operation is accelerated by NQDNN, we will mark it as true. So actually you can see different speed up among different operations. So let us look into the bar chart. It's more easy to understand. So for the y-axis is elapsed time, and we compare among AP32, which is marked as orange bar, and INA is marked as blue bar. So as you can see, most of the blue bar spend less time. There are some operation actually spend Intel TensorFlow spend more time, but actually we will identify that operation are not accelerated by 1DNN later. But as you can see, the top taskbar actually we got a good acceleration by using INA. Then we compare the speed up among different operations, and also we mark the operation which accelerate by 1DNN as blue bar. So as you can see, the orange bar, for the orange bar, most of the orange bar are not don't have a good speed up. It's just below or around the red line. But the blue bar, which are accelerated by 1DN, you can see a good speed up among two operations. One is fuse convolution 2D, the other is 2 TensorFlow. So actually from this comparison, you can understand not all the operation will be benefit by using INA. So at least for convolution and 2 TensorFlow, you have a good speed up, but some operation are not are not accelerated by INA. So that means if you have a related operation, you should be able to have a good speed up.
Your voice is breaking. We can't hear you.
So is that better right now?
No. There is another question for you on the Slack. Could you post the Git or Jupyter notebook links?
Oh, yes. So can you hear me right now?
Yeah.
Sorry for that. I think probably some network issue. Apologize for that. Yeah. So let me, I think it's also in the slide deck, but let me also put the link here.
On the Slack, that would be better.
Okay. So I also put a link in the chat box. Yeah.
Sure. I can copy it for you.
Yep, thank you. So, yeah, so we are mentioning about the pie chart. So for pie chart, you can understand the hotspot between different data type. So you can understand for AP32 and INA, actually they have different hotspot. So basically for INA, we got the good acceleration for convolution 2D. So you may also need to look into other second hotspot, which is fuse mat multiplication. So overall, by this performance analysis, you can understand which TensorFlow operation are benefit by INA data type and how much speed up you can get, and what is the next hotspot you should look into once even you apply INA data type. So same story applied to Bf16. So for Bf16, we compare Bf. Wait a minute, let me enlarge the screen. We compare AP32 with BF16. You can understand how much speed up by using BF16 among different operations. If you look into the bar chart, actually you can see most of the operation actually have a speed up by using BF16. So it's different from in A. So overall for BF16, a lot of operation can benefit by using, well, if you're using BF16, lots of TensorFlow operation can have a speed up. And for this diagram, you can also understand the speed up among different operations. For the blue bar is one DN operation. Actually, a one DN operation have a good speed up, but if you're using BF16. But even for the non-one DN operation, you can also have a good speed up if you're using BF16. You can see actually some metric multiplication, mean or squeeze operation actually also have a speed up. So for BF16, actually many operations can benefit by using BF16 data type. So it's actually quite different from in A. And for the hotspot, actually you can see AP32 and BF16 have pretty similar hotspot. So, okay. So that's for in A and BF16 inference. Any questions so far?
No.
Okay. Then we would like to look into the training part. So for training part, after you run the first Jupyter Notebook by selecting the SNet50, you can get the overall performance analysis. So the first one is the comparison for throughput between AP32 and BF16. I think my network is unstable. Okay. And the second bar chart diagram, you can understand you will have 1.3 times speed up by just using BF16 on ResNet50 training. And then send to the previous result, we also doing the timeline analysis for the BF16 training. So let's look into the comparison table first. So first, first column for sure is operation. You will see more operation involved here in the training. And then we compare the first and the second column is AP32 and the third column BF16 for using NKLDNN. And then let's look into the bar chart. So overall, the y-axis is elapsed time. The x-axis is different operation. The orange bar is AP32. The blue bar is BF16. So as you can see, most of the hotspot, the AP32 spend more time than BF16. And here's the performance speed up comparison. So the blue bar is the operation accelerated by 1 DN. The orange bar actually is operation non-accelerated by 1 DN. So in the training case, you can see if the operation accelerated by 1 DN, most of operation can have a good speed up, except for multiplication. But for the operation not accelerated by 1 DN, most of it are not have a good speed up. So in the training case, 1 DN can give you more speed up among operation. And then for sure, you can have a pie chart to identify the hotspot. Here, we have similar hotspot among AP32 and BF16. So, in short, by running this notebook, you don't need to configure any parameter and you can understand how many speed up you can have from by using Intel TensorFlow, and also how many speed up by changing the data type. So we have Bf16 and InA. You can understand how much speed up you can have. And also you can understand which operation, TensorFlow operation have a good speed up, which are not, and what is the hotspot you need to look into for further optimization. So any questions so far?
No.
Okay, good. Okay, then let's go back to slide deck. So then the final topic we would like to cover is model conversion from AP32 to Bfloat16. So TensorFlow actually have a new feature called Auto Mix Precision. And Intel also provide a new feature called Auto Mix Precision NKL. So basically, it's Auto Mix Precision supported by NKL DNN. So it's a grabber path that help you automatically convert a model written in AP32 to BF16. So you can see a simple example below. So in the right-hand side is AP32 model. So as you can see, for the input, the X, W, and BIOS, the B, they are AP32 data type. And for the operation, convolution 2D, BIOS add, and ReLU, they are also operate in AP32. So by having the auto mix precision NKO, actually TensorFlow will help you to convert the data type to BF16, and then using the BF16 operation to do the calculation. So overall, as you can see in the right-hand side, we will have a cast operation actually convert the AP32 input, AP32 input like XW or B into BF16, and then the convolution 2D BIOS and ReLU will convert, will operate with the BF16 data type for you. And by using BF16 data type, you can see the speed up from what we saw in the Jupyter notebook. So we understand actually for BF16 convolution 2D, for sure we will have a speed up, BIOS, add, and ReLU will also have a speed up. So yeah, you can understand speed up on operation level by using our notebook. So I think I won't cover the last tutorial because for this auto mix precision feature actually is support in TensorFlow. We may not release 2.3 of we may not release Intel TensorFlow 2.3. So I just want to mention this feature, but once we publish it, you will get this speed up automatically. But because right now we may not publish the Intel TensorFlow 2.3, so probably I won't go through the demo. But for sure, if you want to see more detail, here's the article. You can look into that. It also provides a sample code for you. You can just grab the sample code and run it. But for sure, you need to have latest TensorFlow 2.3 with the related implement. So you may maybe you can come back for this topic later. But yeah, but we just let you know. You don't need to do anything. It's there's a grabber path, so it's do it for you automatically. Yeah, I think that is the last topic I have. So
Your voice is breaking again.
Oh, breaking again.
No, it's fine.
Yeah. Okay. So yeah, I think this is the last topic I have. And so we cover what is Intel AI Analytic Toolkit. So overall we have performance library, deep learning framework, and also some benchmarking tool. And we also cover how to analyze deep learning model on Intel Tensorflow. So we have couple Jupyter notebook and help you to identify the hotspot and understand which operation have a good speed up, which are not, and how much speed up you can have from Intel TensorFlow. And we also mentioned about Bf16 support on the latest third generation Xeon server, and also you don't need to do the conversion on the TensorFlow 2.3. It will convert for you automatically. So that's all I have for today. So if you have any questions, welcome to contact us, and we will be great if you can give a try. And that's all.